Okay, so yeah, I'm gonna do a quick summary for the people who joined late. So yeah, what does these things have in common? There's bad tooling. I've been making chips for 15 years. I pretty much use all the tools available before we started GDSFactory. The main reason we started GDSFactory is because the other tools were like 200 times slower and very hard to use. And I was working like in companies like Quantum and Google, where we were making very complex chips. In Intel and HP, I was mostly working on transceivers. They're also complex, but maybe not as complex as the chips we're doing in the last two companies. And then we have over 2 million downloads, like more than 8 developers, and today we'll be doing chip design and verification using GDSFactory. And you just need to go to this URL, and then you will be able to follow the workshop. So yeah, in the workshop it will be mostly you doing following the instructions. So we have this quick start guide. If you want to also look at the documentation, so if you go to gdsfactory.com, there will be, it's also documented here. So we're going to be using GDSFactory Plus, which is the GUI for GDSFactory that will make the whole workshop a bit easier. And yeah, we have two options for the workshop. Like you can run it locally on your computer, but if you also have like old computer with not a good RAM, like for example, I'm using a Mac, a new MacBook Air, so it's very fast on my computer. So I'm gonna run it locally. But if you have like maybe an old computer with not enough RAM, or you find it's very slow, I'm gonna also give you an option of running the workshop on a cloud version. So, and it's all in the, once you go into the instructions here, you go to GDSFactory Plus, it's, if you go to quick start, this is the same as gdsfactory.com/workshop. So yeah, for like if you guys want, we can do the cloud one too. Like there will be two options. So when you do the workshop, you have two options. You will do the workshop or the local setup. So if you have like a Mac or a powerful computer, I recommend local. But if you don't have a Mac or a powerful computer, I recommend doing the cloud version. So if you go to the cloud version, you basically will do it on your browser. So you need to log in into this website. I think I already correct. You will need to put this user and password, and then it will basically create a cloud workspace. But yeah, if you also want to run it locally, it will be just go to local setup. So once you're set up, like what you should see is like I have it here open. So the first thing we're gonna be doing is a parametric cell, and we're gonna do this hello world. I'm gonna click the pencil to edit, and I'm gonna be I'm gonna write, instead of hello world, I'm gonna hello U of T. And then I will save, and I will see here. I can do Toronto, maybe that will fit. So this is what you will see after you file, open folder, and then open the folder that you downloaded. If you did it local, if you did it on the cloud, it will look like a. Let me show my computer. If you do it remote, I already log in, but it will be like already signed in. So workspaces, you will have a workspace like this. Oh no, sorry. Let me show. It's a private window, so you don't see. So you will see something like this. Let me just log out so you can see the same thing. You will sign in, and it will be demo.gmatres.com and then demo 2025 exclamation mark. And then you just need to workspaces and then create a workspace, and then you should put your name, like so you can who are you. I'm gonna just put Joaquin Matres, and I'm gonna create a workspace. And this is gonna take like from 1 minute to 2 minutes. And once the workspace starts, you can click on the link, and this will take you to a VS Code running on the cloud, where you can actually do the work for the workshop. So I usually recommend you have like 2 windows. Like one will be this outline, and then the other one like will be the other window. So you could do something like this, like divide the screen into 2. Or you can also just go from one to another. I have a few monitors, so I could put the other one in the other monitor, but yeah. And then you will open this hello world, and then you will be like, I will modify, for example, like, let me close this. I'm going to be here, show GDS, and I'm going to modify hello world by hello.
Sorry to interrupt, Joaquin. It seems like a lot of the people in the chat are asking about the password that you used for the demo.
Oh, yeah. I put it, like, you may need to refresh. I just put it in before the workshop started. So, like, it's, go back to the, like, let's go back to the cloud workspace. You should be able to see. Let's go to the guide. So it's, I put it here, and the cloud workspace, it's demo 2025, and it's, let me see where I put it. No, it's a quick start guide. It's at the GDSFactory workshop. It's, the website is prod, like production, gdsfactory.com. Is the user is demo at jmatter.com, and this is demo 2025. If you open the website before I put the password, you just need to refresh. But
Yeah, can confirm it's working now. Thanks a lot.
And yeah, like but yeah, if you're doing the local installation, you don't need to do this. So for the local installation, you're gonna use it locally. So it will look more like my screen here. One option. So yeah, once you finish the Hello Toronto, I think if you can raise your hand, that way we can know if we can move on. Or if you have any questions, I'll be happy to take a look. Or you can, if you have any issues on the chat, you can share with us. Like one of the challenges of doing this workshop remotely is that if you have any problems during the installation, it may be hard for us to help. But if you could maybe send a message or a chat, we can capture it. We also have at the end of the section, we have like in the workshop, we have it's part of the quick start guide. We have this debugging section in case you have problems during the installation. But if you have even problems there, you can copy paste your errors in this report errors here. So this could be something that you could copy paste the error that you have, or you can put it in the chat. It's up to you. But yeah, some of the things on remote workshops is that if there is any IT issues, it may be hard to see. And I think some people are having problem with the creating workspace. No, it says stop in some of them. So maybe the local version may be more reliable. I don't know how many new workspaces we can have.
Looks like we have a few more questions in the chat from Vincent and Amar.
Oh, yeah. Okay, Mateo has, I see the question now. I think Mateo had a question, like the edit GFP key. I don't think my email is verified with GDSFactory, but you don't have to create a user. So I already created the user and the password for both the local and the cloud. Once you do the local, what you're gonna do is you're gonna do like well, like I can, if you guys want, I can restart my screen so you guys can see. So let me restart my extension so you will see what happens. The first thing you need to put is the GDSFactory plus config. So this is where you're gonna put the key. But you notice that the key here that we put, it has these brackets. So you need to grab the key from the from the document that we put it in. So if you go to the GDSFactory Quick Start Guide, the local setup, we put the key here at the end. And then you can copy this content, and then you can put it into this 3 dots. I think I put there was an extra dot. Sorry, I didn't put it in the right place. I should copy paste everything. Now I save, and then you can see it automatically detects the key. And because I already file open folder this project, it will like install. Then you need to make sure the version matches the GDSFactory. So I have the same version in GDSFactory on the GUI, and the library needs to match. Then you will see that they will build the foundry components here at the bottom left, and it will be the project components on the top left. So you see, like I can click off any of the components here. Like this is a straight rip, C-band and O-band. You can see like a die. So and here you can see some of the example that we've done. Like for example, we have examples on how to do like automatic routing. So you can see I can move the instances and it will automatically route. We have examples on like DRC errors that we will be doing. what we're gonna be doing is basically the first one is this sample parametric cell, example hello world that you modify, and then we will do a rings filter. So I see some questions about related to virtual environments. You don't have to worry about any of that. The software will automatically create a virtual environment. So that's the window that it came up when I start a window, when I start the app, it will check that you have the valid virtual environment, that you have the key, and then the library matches the version. So you can see it initializes everything. And what this is doing is creating a virtual environment for you to work. Like if I look at the project, it creates this virtual environment. Yeah. Yeah, so if a lot of people has problem with the IT, like I can also show it on my computer. But I think it's usually more helpful for you to follow and try to do it yourself. But yeah, I understand like if it's the first time using VS Code or like using GDSFactory Plus, it's like everything is like the first time maybe hard to get used to new setup.
I mean, if anyone is struggling with anything in particular, I can also jump in and like have a look.
Yeah. Thank you, JD.
So just let me know if, I don't know whether we can set up breakout sessions, but we can think of that if that's possible.
Yeah, I don't know if we have breakout sessions. I think Zoom has breakout sessions. Yeah, breakout rooms. Oh, cool.
So if anyone wants personal support, let me know and we can go to a breakout session.
Yeah, JD is also one of the creators of GDSFactory, so yeah. Okay, specify the Python environment. Yeah, and like all these Python environment issues, it should be automatically created. So once you open the file, open the folder, and you have GDSFactory Plus, it will automatically create this virtual environment. So you don't have to worry about what version of Python. It will automatically download Python 3.12 for you.
Yeah, I think they're saying something doesn't seem to work automatically. So maybe.
It depends. Like sometimes we notice like if someone has like a Anaconda and it's not automatic. Okay, yeah. So
Yeah, okay, so maybe we can have a closer look at that while you go on with the other people. If you can put me in a breakout session with
yeah.
Matteo or Apai.
Okay, yeah. Let me create a. I'm also not super familiar with Zoom, but I think I saw it. Breakout rooms. So okay, there's room 1, room 2, 3, and room 4. Okay, nice. So I'll assign DD to room 1 and then Matteo to room 1. If anyone wants to join. Okay. Oh, okay. People can join themselves, or Abe also join. Yeah, Tony was just saying how he fixed it. Oh, the link not showing up. Yeah, like you may need to create a new one. Like sometimes I find like if multiple people try to create a workspace exactly at the same time, it may fail. I'm using the online version, but just create a. It's not showing up. Should I keep waiting? Oh, yeah. Maybe try to create a new one if the other one didn't show up. Or like maybe try the local. Otherwise, I can also show it on my computer. Like if I show it on my computer, we may be able to go faster and then cover more content. So that may be also interesting. We can try this if people have problems. We will have another one at UCSB on Thursday, so we can also. You will have also like a few days until the next workshop to try to figure out the local deployment. But I'm gonna be moving to the second part. So we finished like the first part of the workshop was the local setup, but some people went with the cloud, and it seems like cloud may be having some issues for some people. So I'm gonna just we already did this parametric cell. So after we did it, created a parametric cell. We can create one, also a new one, so you guys can see. So what you need to do is that you hit plus, and then create a Python layout. And I'm gonna put hello Toronto, and then I'm gonna paste here the code. And then what I will have here is that I can show the GDS. So here is hello world, but I'm gonna change it by Toronto. So this is a parametric cell. And this parametric cell has like any parameter, you can make it a parametric value. It could be things like size equals 10. And it could be, for example, the size, that could be size. So I can, by checking only one number, I can, like, let's say I can make 100, then suddenly everything becomes bigger. So you can, with a ruler, I can measure, this is 100, this, every letter is 100 microns in size. So this is the first part of the creating a parametric cell. We have more examples on other types of parametric cells. You can also do it later at your own time. The second part of after we do this is gonna be designing the first circuit. Okay, someone got the extension installed next. So we have videos for all this also, but what we're gonna be doing is going to the PDK menu. Then we will create new schematic, and then we will define the schematic and add the routes. So this is what it's gonna be. It's gonna be 2 ring filters. So I'm gonna do it on my computer, and then you guys can follow to also the detailed instruction. So I'm gonna do create new schematic, and I'm gonna call it rings filter demo. And once you go into the schematic, if you press H, you will see all the commands available. So the first thing I'm gonna press I to insert, and I'm gonna insert a first ring called R1, and it's gonna be a ring single SC. So S means strip, C is for C-band. So I have a first ring here, and I'm gonna press here R2, and I'm gonna add a second ring. And now if I do show GDS, you will see there are two rings. They're actually on top of each other because I haven't defined any placement. So what I can do is I can move instance, and I can move the instance anywhere I want. So I can move this instance to the right, this instance to the left, and I can define a route. You can define route with two options. So you have the way to define with link. You can define a logical link, or you can define a route with B if you want to define multiple routes. B is for bundling. But once you create a logical link, it means that I want to connect this to this, but this is just to show your intent. Then I turn this into a route. And here you can configure the cross-section. I'm going to use the default one, strip CBAN. Then I save it, and they automatically connected. And because they're connected in the schematic, even if I change the layout, the route will follow. And then I'm going to add P for port. I'm going to put an input port and an output port. And then I'm going to do link. And I'm going to connect the input to here and the output to there. And once I have ports, I can do control save if I want to save faster, but you can see the ports will be here. And then I can do simulate, circuit, and plot. So I can simulate the circuit directly from the schematic, and I can see the ring resonance. Now that the two rings are exactly the same radius, so the free spectral range of the filter is the same, so they filter the same frequencies. But I can modify one, so I can press E for edit, change the radius to 11, save, control save or command S if you're Mac, and then I can do another simulation. And then if I change the second ring, it will have a vernier effect. So this is what you will see. The nice thing of this is that once I have this defined, I can put it into another hierarchy level, and I can do many of these, or I can do ring filter 2, and then I can create a schematic with this one that has many of the first ones. So I can create the ring filter 2 can have a combination of multiple ring filter 1. So ring filter demo is the first one we made. I can put one here, and I can put another one. And I can use like something like C to connect directly. Connected means that it's physically connected. So if I show the GDS, you will see that the ports are connected one to another one. And if I hit show ports, it doesn't have any ports because if I want to expose this again, I need to still add ports. So ports allow you to do simulations as well as hierarchical components. But you can do as many hierarchy levels as you need. So this will help you like make complex circuits where you have small pieces and then you can connect them together to make more complexity. So yeah, the C was the connection. I can also delete it, and I can also define if I delete it, both of them are on top of each other, but I can move one to here, or if I right click, it will rotate. So it's also a nice way to connect. And now I can use a different letter. So I can use like a link, or I can use bundle. Bundle will already create a link directly. So I can do P. I can do a link, and then connect to the route. If you have multiple routes, you can use the bundle because then you don't have to click so many times to turn it into a route. But yeah, this will maintain the route. Yeah, it's a question. Can you define materials for the P cells? Yeah, that's a very good question. Like we did one for this hello wall. We also did. You can see here what we changed. So we create this sample 0. So sample 0, we already defined like one text, but in hello world we actually make even more changes. So we define a material. You mean material? I assume you mean like layer, because every layer in GDSFactory, it maps to a material. So for those who are like new to chip design, I also recommend going through the GDSFactory tutorial, where we have the concept of this generic PDK. So in chip design, every layer it's like a building. So every layer represents one level of the building or one fabrication process, or some levels, some building floors can be defined with multiple layers. Because some of them mean grow, some of them edge, some of them mean dope. So there's different processes. And in the end, you need to define like every layer, what's the thicknesses and the starting height, as well as the sidewall angle. And once you have that defined, you can turn your chips into 3D objects. Like for example, this is a grating coupler antenna. So this basically takes the light here and diffracts it into free space. So this can be used to couple to a fiber, or to couple to free space like a LiDAR. This is another interesting structure where it works as a heater. So as you apply current through the heater, it basically heats up the waveguide and changes the speed of light. This is also available in we could do a more advanced workshop where we cover all these, designing all these components. And this is another type of heater. So this one is a metal heater. So every layer you could change. So for example, let's say this hello Toronto, we're going to change the layer as well. So let's go back to the PDK, and then we do sample hello world. Let's look at what layers were being used. So we are using only layer 1 and layer 2. But what we could do is that we could change any of these layers. So let's say, for example, let's change Toronto to 3. And then I save it, and automatically shows. And you see this once the layer is defined in the layer map, so it means that we can define the color. So this layer 30, it has a meaning in this process. So it means waveguide. So if you draw something on this layer, it will mean that this needs to be this will be fabricated in the waveguide layer, which is usually the silicon layer. Yeah, this will also affect the simulation results. Like one of the advantages of GDSFactory is that directly drive the simulation. So we have also here some examples, sample notebooks where we have this training. So let's say we want to drive a simulation of a heater from the layout. So this is using an extension, like an FEM extension, where we define the geometry layout. So this is basically, you can see this in 3D. So this is a waveguide heater. As you apply current through the heater, it changes the refractive index. There's a thermoptic coefficient as the light travels through this waveguide because of the heater above. You can see the heater has like connections for input and output. And as you flow current through this metal heater, it will change. There's a thermoptic coefficient. And you can see I can sweep the current and I can very fast calculate the effective index. So this will give me like for example, like a 5 phase shift. So, but if I change any of the parameters of the circuit, for example, let's change the box from 3 to 2, and then I will have the lower thermo-optic coefficient. So this is like one of the examples where changing the values of some of the layers or some of the layer stack values will affect the simulation results. We have also an advanced section on routing that I can also show. We also have videos, but if you guys, we can show this part too before we jump into the third milestone. I can save this one for the routing. We have examples on how to route components. So we can show, for example, like let's do like this lattice filter. We can move the instance and it automatically will route. Something you can also do is you can also simulate this circuit. Like for simulating the circuit, you do simulate and simulate circuit and plot. So this shows the frequency response of this filter. Another thing that if you want to optimize the circuit, sometimes you want to change the parameters. So we can easily turn this into a Jupyter notebook. And this will show me the schematic, the layout, and the simulation. So a lot of times when you're trying to optimize the circuit, you don't want to reproduce it again. Like similar to simulations, if you're doing this layout or like this schematic, you will automatically be able to drive the simulation. So you can do that using Jupyter notebooks. So I can turn this circuit into a Jupyter notebook. Create new comment. Yeah, I think someone has a question. Like Karen has a problem when you define material. When I create another project, create a new project. It's something that we added, but it's not fully supported. That's what I kind of like. We provided you with this example project. If you want to use GDSFactory plus with other like projects, like I think you can contact us. This is most of our workshop, so that's why we created this example project where we have example circuits. But if you want to create different projects, I think this is a bit beyond the scope of today's workshop. So as I was saying, like we can import the circuit and then you can turn it into a GDSFactory component. This is the same component I'm here on the right. Extract the netlist and I can simulate the circuit. And you see it's very, very fast. And one of the things that these notebooks allows me is that I could change the simulation parameters, or I could change the value of the circuit. We have an example of a circuit optimization that I could show you if we have extra time. But like for example, I can change instead of 15, like 1.50, this is 1.50 to 1.60. So you see from 1.5 to 1.6, I could start at a shorter wavelength, like 1.5, 1.45. And you see I have more wavelength range on my sweep. So this covers like simulation of devices, simulation of circuits, and a bit of like advanced routing. And the last part of today will be the verification. And there are different types of verification. So when you fabricate chips, like chips can be expensive. Like if you look at your iPhone or your computer, chips are probably costing, like every chip will be like, just to make one, it will be millions of dollars, because you need to make the masks, the molds to make the chips. But once you have the molds, making more and more chips is very cheap, like because you benefit from the economies of scale. So what we're gonna be making sure is that you don't make any mistakes, because if you make a mistake on making a chip and it costs $1 million, then maybe your company will crash. If you're in a small company, but if you're at a university, maybe it's okay. So I think if you think about, maybe now it's okay not to run verification when you're part of a company, it will become more and more critical to make sure the chips are correct, because you have a limited amount of iterations that your company can afford. So we're going to be opening this file called errors.py. And here we have an example of errors. So when I run DRC, like you can see, like I can see, for example, like this, I'm using like component. Yeah, let me make sure I have the same as you. Let me revert this. We have I made some modification before the workshop, but maybe let's just show exactly the one you have. So if I look at the code and then I show GDS, something you can do is that you can easily, if you type error, like, or have any typo when you're coding, and let's say you have some undefined variable here, the moment you save, it will automatically go red. So this means that you have an error in this errors file. And then you can look at the logs and it will tell you, hey, this is not defined. And then you can click and it will automatically bring you to the error. And I save it, and goes back to green. So that means it's correct. So when you're doing like chip design, it's very important to be able to show the GDS. And this GDS, this Python file has multiple like parametric cells. I mean, they're fixed cells. They're not really parametric because we don't have any parameter as an input. But I can show any of them, and the same way that I can run DRC on any of the cells. Like I could run DRC on only one cell. But these are different chiplets. And let's say you have a computer chip. Like these days, all computers have multiple chiplets, and you want to make sure all these chiplets are clean, are ready for fabrication. So you can go here to the top right, DRC, and then check DRC. So DRC means design rule checking. So if you bring things too close to each other, the foundry, when they fabricate the chip, are not going to be able to distinguish them. So they're going to be merged. So this is a risk because I wanted to have two pieces of metal or two pieces of silicon in this case, and I want them to be separately. But if the foundry cannot separate them because they're too close, I can measure here, the distance here is 100 nanometer. So like, this is not allowed by this foundry, like Cornerstone. So if I click in the minimum space, it will highlight all the errors. So 1, 2, 3, 4, 5 minimum space errors. And when you're cleaning DRC, it's an iterative process where it's useful to be able to see your source code and your result. I can minimize this if I want. So I know that in this errors py, I'm making a variation of the gap from 100 to 200. So I can change it from 200 to 400. I save it, and you see they all change, except we have one here left, which is coming from this separation. Then I can save it, and now this is still like, there's still one gap min here. Yeah, now all of them are fixed. So once you fix these errors, we also have another type of error. Like, I don't know if you remember here, we have an error on the minimum width, and this minimum width it was highlighting this shape, but because I changed the thing, they moved somewhere else. But I can also change this with min to size equal 0.2, 0.2, and I save it, and now it grows. So now I'm gonna run again. So I think I fixed most of the errors, but you need to check again. It's not like you should always run multiple times. There's a question. Yeah. So okay. So yeah, we fixed most of the errors. There's still one error on the minimum width. So I think maybe I forgot to modify this one. Maybe gap min. Yeah, the question from Tuhin is that are the built-in solvers mode, chart, hit, custom, or from Tidy3D? So if you go to the notebooks, so like this is also a bit advanced. We could maybe, yeah, I think we have a few more time. I think the workshop was like we have some more time, so we can maybe jump into the simulation. So we have different extensions. So GDSFactory has extension to many tools. Like for example, like FemWell is a finite element mode solver and a heat solver, a multiphysics solver. So this one it's open source and it's included here. So you don't need the Tidy3D. But we also have interfaces for numerical, Tidy3D, as well as MIP, and also luminescent AI. We have interfaces to many other tools. So this allows you directly from GDSFactory to run a simulation in numerical. And we have a very similar interface to also do the same thing with like Tidy3D and MIP and all the other solvers. So that way you can choose the best solver for your needs. So yeah, this is the Tidy3D one. It's the same. If you run this notebook directly from the layout, it will create a this is the same thing. It just creates a layout, turns it into a simulation object, and then you can simulate and get these parameters. But yeah, if you want to go deeper into this, so we have, if we go to the GDSFactory, you can see all the plugins. So these are extensions that we have to different tools. And as I was mentioning, we have Tidy3D, Lumerical, Luminescent AI. There's also FTGZ, which is the MIP. So yeah, it's a very good amount of solvers just for FTD. But for small solvers, we have similar. So we have a finite element. We have Tidy3D also has their own solver. MPB is the one from MIP. And then we have our EME as well with Meow. So yeah, this goes a bit more into like device design. So for circuit design, we use the circuit solver SAX that I was mentioning before. That is also very powerful. You can do things like Monte Carlo, like to variability, to make sure your devices yield. So yeah, all these notebooks are also in the sample project, so you can also explore. And yeah, we already did a device design. If you guys want, we can also jump into like a circuit optimization, and that may be also a good example. Or we can also have a Q&A where if you have any questions or capabilities, I could show them. Yeah, feel free to put in the chat any questions or things that you want to know if it's possible or not possible, or any advice.
Yeah, hey Joaquin. So we're back from the breakout session. We have managed to install UV. It was a bit of a ride. I don't know. But I think if you could maybe give some pointers to what has happened in the last, I don't know, half an hour or so,
Yeah.
it would be nice.
Yeah, we could do recap.
Okay.
Yeah, that's a good point. Yeah, like so the first thing we did is we created a parametric cell. So I assume some people were able to install it. Maybe some of them have technical problems. The session is also recorded, so people can also watch it later. But like the first thing we did is that we went to this sample hello world. So we were able to, if you hit the pencil, you can visualize the code that creates the design, and I can do show GDS. So one of the questions was like if we can change the layer, so the layer can be changed here as part of the layer parameter of the components. This allows you to also visualize the chip in 3D. So we also have this show in 3D, so you can visualize it in 3D. You can also put like parameters here where we did size like 10, and then we put this size as part of the size of the text. So I save it, and then I can increase it to maybe like 50. This allows you to do like any parameter, and you say that the text will grow from 10 to 50. The second part, like we created a schematic. So I call it rings filter demo sample. Just choose a different name. When you go into the schematic mode, if you press H, you can see all the commands. So this is a model editor. So you need to press a key like I to insert, and then you can type like ring 1, ring single IC. I put a ring here, I put another ring there. Because the rings, you can define the placement, or you can make an array of rings if you want. The placement, you can define it here. So I can do like a 20, and then I can show it in the GDS, and they will show side by side. But you can see 20 is not enough. So I can move it a little bit more to the right. You can, if you press move instances, you can actually move it. And what that is updates the placement. So I move not only in X from 20 to 37, but move it also in Y. And then I press link to create a link, and then create a logical link. A logical link can be turned into a connection, which is a physical connection. Like I can save it so you guys can see. This will connect the ports to each other. Or it could be, if I press delete and delete the route, this could be connected into automatic. Like, let me go back. So now we have the original placements. I can turn this into a route. And this is an automatic route with bends and straights. And you see it created an automatic route. And I can move the instance up and down. And because they're defining the schematic, the layout will match the schematic because it's a schematic-driven layout. Notice that this won't work in Python. Like if you define this in Python, like if you define it in Python with automatic routes, it will work. But if you define it with Python with a combination of bends and straights, which I don't usually recommend, then you have to define them again if you change the location. So now that we have done this, so we added the P. Like if you go back to like the schematic, like you can go to P for port, define an input and an output port, and then press L to link, and then show ports. So the ports are not a physical thing. They are basically an abstract construct to be able to connect things or excite the device level simulation or excite the circuit level simulation. And this allows you to do simulate, circuit, and plot. And you can see it's very fast. It finished in less than a second. And then I can see the spectrum. Another thing I could do, I could change the values of the circuit. For example, I can change the second ring. Let me change the radius. Let me press E. I will change the radius from 10 to 11. I save, and then it will, I don't know if you noticed, but it grew by 1 micron. And if I do another simulation, the two rings have slightly different frequency repetitions. This is called the free spectral range. And they only line up at one wavelength now. Something we also show is to turn this directly into a notebook in case you want to do optimization. So this will turn directly the circuit into a Jupyter notebook where I can customize the parameters or the models, and then I can visualize the layout as well as the circuit response. And once you define the circuit response, like for example, I don't know if you notice here on the right, we don't have enough points, but I can increase the resolution by adding more points. Like let's do 10 times more. You see, it's very, very fast. I mean, let me zoom in now. So from 1.6 to 156 to 160. Let me do 156. So you see, now you see very well resolved resonances. And you can also see the phase. And you can see every resonance has a phase change. And this can help you differentiate versus overcouple versus undercouple rings. So yeah, this is directly from the schematic. I can drive the circuit simulation. I can define the layout. It's very convenient. Or I can define hierarchical components. Like we put this into like a, let's put it into a die. Let's put a die with rings. Sample. And then I can just put like the R ring single. I think we put a ring filter demo. To put it here, and I can also put like a die. And then I can show the GDS, and then you can see the rings here. I can move them a little bit closer to the side. So it's very easy to do, like move it somewhere I want, like here, and then I could connect it with the green couplers from the die. And yeah, it's a very convenient way to define circuits. I think then someone had a question about device level simulation, so we went to this notebook. So we did this heater optimization and heater simulation. We basically solved the different currents, and for a heater, like we calculate the thermal distribution, and then as we have different thermal optic coefficient, we have different phase shift. So that's then what we did is we did the milestone 3, which is focusing on verification of circuits. So we went to this errors file, and then I can maybe revert it because I remove a bunch of errors. So because everything is in Git, it's very easy for me to know what we did on the workshop. So I knew how I fixed it, but I can just, if I want to go back, delete, I can discard the changes, and then we have the errors are back. And I run the ERC, and then it will check the ERC with the Foundry rules. And this is all very convenient because it's all in the same ID. Like you can see, for example, we have 5 minimum space errors, and we have 1 minimum width error. And yeah, and then we went in the code and then fixed these errors by updating the parameters, because the problem is that as you read the error, the minimum space is 0.2 micron, and here we are at 0.1. So yeah, this may not be resolved by the Foundry. So it's like 3D printing. If in 3D printing, if you bring two objects too close to each other, they will merge, and this can be a very bad error. If you have like you could create like a short or an open. So yeah, this is something the Foundry doesn't allow. And yeah, like at the end of the workshop, we also have like a survey. So if you also have time at the end of the workshop, it may be also good, so we can understand like what went well, what could be improved. So the next workshop could also go at the end of these sample errors. This is what we did, cleaning the errors. Yeah, and then we have here the feedback form. So this could also help us improve like future workshops. We've been doing almost a workshop every week. Some of them will be available in Zoom, like today's workshop. The one on Thursday at UCSB will be both in person and remote, so that may be a bit tricky. We'll see how it goes. And I think they have another one in a couple of weeks in UCL. So there's a lot of European universities joining that one. Oh yeah, if you sign up for this, we could keep you on the loop for any future workshops. The best way is to follow us on LinkedIn. Like in LinkedIn, we make posts and then we make also calendar invites. And if the calendar invites includes the Zoom link, that means that the workshop will be also available on Zoom. Some of them are in person only. Like we had one in Stanford like a few weeks ago, but the one at MIT like also a few weeks ago was also fully remote. Actually, no, it was half. It was half people remote, half people were in person. Yeah, and also I also want to mention that we have a lot of videos, not only in the quick start guide, but the videos are also available here. So this could also help you follow through the work. Like today, it was a lot of content, so it may take time to learn because, for example, we have universities who are using this as like a course material, and this is like kind of like we have course material here for like a whole year of lectures, but today we were trying to condensate in a short amount of time. So you watching these videos at your own pace may help you like better understand the concepts. And like it's like everything in life, you just need to practice and do more and more chips. And if you want to contribute, we also welcome contribution. Like this project is this CSPDK is open source. And the sample project is also open. So if you want to, for example, here I'm working on a branch. I was trying to fix the lighter, but you can create a new branch. I was trying to put that together a lighter example this morning, but yeah, it was a very short time, so I stick with the part that we had before. But you could do here like a improvement, create a branch, and now when you're on a branch, you can basically fork and push to your branch, and then you can try to merge request into the original repo if you want to contribute. If not, it's also totally fine. Oh yeah, just look for GD. Someone is asking for the GDSFactory page on LinkedIn. I can put it here. It's basically just follow GDSFactory. I can, if you look at it. We're also going to start a mailing list. So keep an eye on the website. So we will have a mailing list soon. That way you can also know what workshops are going to be coming. So yeah, let me put it here. Yeah, and if you want to find other types of verification, also that may be also interesting to see. Like today we were mostly the DRC, like design rule checking, but there's other types of verification. For example, we have when you do chips, you can have something like this where you have a connectivity error, So if you go to the DRC, you can check connectivity as well. So this will help you find errors. And here is very obvious because we only have 4 chiplets that they short each other. But if I go by category, I can see that the instances are overlapping. And there's another type of error called layout versus schematic. So if you have something like this, like let me show the layout, and then let me show you the GDS also, so you can see. Let me put it side by side. So here I make a very simple like LVS error. So I have a straight connected to a bend, and I connect the straight to the bend, and then I say, oh, this also need to be connected, which is not possible. And this will trigger a LVS error. So if I do DRC LVS, it will show you, hey, you say that everything needs to be connected with everything, but it's not really connected. Like there's a missing connection between here and there. So it is a layout, the layout versus schematic. So layout you can think as the implementation. So implementation is like the building of a house, and the schematic is the map. Like if the map doesn't match the physical layout, then we have a problem, because when you are doing like chip architecture, you may have a very complex chip with like thousands of components, and you can think of it also in terms of constructing a building. You have 1,000 of floors, many structures, many rooms, and then some of the rooms may be missing a pipe, and then that's a problem. Like if you think like 2 things are connected, 2 floors are connected, but there's no really connection between them, then the whole thing may not work. So these are why LVS errors are also very important. But yeah, these are like things that you will learn as you do more and more chips, as you grow in complexity, like things that you think, oh, I can check this by eye. Yeah, once you are into like hundreds or thousands of components, then it becomes impossible for a human to check by eye, or you may be missing like very important errors. And as I said before, these chips can cost like millions of dollars. So you want to make sure there's no errors in that. And it's not only the money, it's also the time. It takes almost like a year to make one of these fabrication, testing, packaging cycles.
Like someone has their hand raised.
Oh yeah, okay. Yeah.
Sorry, I have a question. Is the other way around works? So if I manually draw a waveguide between the 2 components, will the connection be reflected in the schematics?
You're trying to extract the schematic from the layout, from a Python cell? Like, is that what you're trying to do?
Like, yes, I guess so. If I imagine if I have 2 rings and then I manually create a special kind of waveguide, it's still routing waveguide, but connect to 2 components. And if I go back to the schematic screen, will I see that connection there?
Yeah, we have built that functionality. I usually, like let's say you want to do a very complex chip that maybe it's hard to define in schematic, and then you do it in Python. But then the problem is that you're doing implementation, but you don't have a map of the building. Like you are trying to just draw the whole building by your intuition. We have an option that can do that. It's a little bit like, for example, let's say you have this MCI2. So let's. I don't know if you notice when you have a schematic symbols, this means that this is a schematic. But let's go to one that doesn't have a schematic. Let's go to MCI3. This actually has an error, and this is to show. Like something we have is that you can. We're gonna. I mean, you can do it in. We have a version that is gonna come soon that is gonna be able to freeze, extract the schematic directly from the layout. The problem is that because this is not schematic driven layout, this is layout driven schematic, the other way around that electronics people do, then they're not really coupled. Like you can modify the waveguides or do things, but maybe things are not connected. Like this is kind of like one of the dangers of doing it this way. But on the other hand, if you do what we did today, which is schematic driven layout, that you basically, we started with a schematic, like we did kind of like something similar to this lattice. The layout will try to maintain the connectivity as defined in the schematic. So if you are doing pure Python layout, you need to do a schematic separately. And the problem is that how do you make sure they are in sync? It adds extra work. So it's only recommended when you cannot do it like this way. I don't know if it makes sense.
Yes, thanks.
Yeah, if you go to very complex circuits, I highly recommend also, as I showed before, like we went to die with rings. You're gonna have to do like multiple levels of hierarchy. So here we have a ring, and then we put it into this ring filter demo sample, and then we put it into another third level of hierarchy. And this allows you to scale up complexity without like running out of CPU on your brain. And all the cells are still accessible here. So you can go cells. If I go to we have the different cells available. So you can see what it's a full hierarchical cell. So you can see the die rings here still has all the, it will have all, the GDS will have all the hierarchy levels as well. But yeah, if you look at how electronics works, electronics have very weird transistors. So it's very hard for the people just to draw layout. So they always start with architecture. In photonics, because you can see a little bit of what's going on. You can see, for example, what I did before is it's a ring filter. It's not too hard to follow. So some people skip the schematic step traditionally, and they skip it because you don't get any value. Like I did this myself, like for like many years, making chips with no schematics, and you just do layout. The problem is that then you don't really get the circuit simulations or the layout versus schematic. And then if you have like shorts or opens or waveguides overlapping, sometimes DRC won't catch them, and then your chip doesn't work. And yeah, and if you tell this to an electronics person, they will say, yeah, of course, it doesn't work because you didn't check versus the schematic. And I didn't do the schematic because I was always extra work. But now we have a schematic that can give you not only the layout for free, but it will give you the simulation, which is another type of verification. It's like, will my chip work when it comes back? And then you can see, okay, this is how I expect it to work. And if you want to either build in like variability from the foundry, you can do it. You just need to build like more like models where you add like variability, like width and height. And you can study things like tolerances, like yield. So this gets a bit more advanced, but yeah. Okay, any more questions? I think, I can show also like maybe the 3D. I think it's also kind of cool. So you can also filter components, or you can do filter heater. You can look at the heater, for example. I think this also looks very cool on 3D. So you can see the top view, and then you can see the different layers, how they 3D print. And yeah, if you also want to play with the software a little bit more, we can also leave a few more weeks for you to play with it, and then you can experiment with some of the circuits that we didn't cover today. But yeah, and if you also want to join future workshops, maybe also a nice way. But we usually cover very similar content, so it's only in the workshops that are a bit longer. Like sometimes we do into like circuit design, like like circuit optimization, how to optimize the circuit. There's also something that you can optimize the wavelength of a filter. Yeah, we have many examples that we could cover, as well as all the integration with other tools. This one is also pretty cool. Okay, you can take a Mach Zehnder with a heater, and you can just visualize the sub-elements of the circuit, and you can interactively modify the delay between the two arms of the Mach Zehnder, and this will give you the frequency response, and then you can target a particular wavelength and then do like a gradient descent optimization. Then this will basically bring it to exactly the wavelength that we wanted. And yeah, and we will give you the layout, and we can show it in 3D. This is a filter that basically has paths. So with the paths, you can reconfigure the wavelength. So it's a tunable filter. You can see here. You can also do like as I showed before, show 3D, and it will show the same thing, like the circuit in 3D. And this is something you can 3D print into STL, or you can also use that height for defining like device level simulations as we did before. I think someone like John, why you still have the hand raised? Do you still have a question?
I have another question. When I'm an IPKeys user and when I auto routing between two components, sometimes I get snapping errors. Just wonder if GDSFactory, there's any special treatment to prevent this happening.
Yeah, I also used IPKeys for many years before we made GDSFactory. Yeah, we basically got rid of the snapping errors with there are two things. We have actually a tutorial specifically for that. So if you go to GDSFactory, so the snapping errors are basically covered as part of the layout tutorial, and they're a bit of an advanced concept. So people who are like new to layout maybe won't see this until the end of this tutorial. But what's happening is that you have probably waveguides or ports that are not in like Manhattan orientation, like 0, 90, 180, 270. So what happens is that GDS snaps to grid. So everything in GDS needs to have 1 nanometer. You can see the grid here is in gray. All these points, all these polygons will need to snap to grid. And what happens is that if you do like off angle transformations, the points can end up in different points, and then you have gaps. So we have two ways to, and they're like you can see if you have a higher like grid, like database units, the effect is even more obvious. So if you don't do if you do the regular way, you can have this, but we have a way for you to fix them. So we have something that's called virtual instance. So by default, GDSFactory will snap everything to grid, to 1 nanometer grid, unless you tell them to snap later. Like if you create different hierarchical levels, the snapping can build up. So if you create a virtual instance, it will snap at the end. So that will make sure that the only snap in one place, so they don't accumulate random errors. And you can fix these errors by doing this virtual instance. And we have also a version of the components that have the option of having an all angle. So this virtual cell will get rid of these errors by snapping at the end. But yeah, we have actually automatic router that will do like in all angles. So this is very obvious when you start doing like things like this, like all angle routing in diagonals. Yeah, I highly recommend taking a look at all these tutorials. And yeah, the biggest difference when you use GDSFactory coming from like an IPKeys is that you will notice that everything is very simple. Like you need very few lines of code to do things. For example, like today we were showing this sample wall. In a hello world example we did, it's just like 10 lines. You can define a component, add some references, move the references position, rotate them. And it's very simple. You don't need to define classes. You just need to define a function that takes some input parameters, and it always returns a component. So you can think of, you have a canvas, you draw on your canvas either polygons or shapes, or reference to other canvas with rotations or xmin or translations, and it returns that. You don't need to define like a complex class. So it will keep your code much simpler and easier to work with other people. But yeah, it's like everything. Like usually changing tools requires some effort and also some kind of like investment. So I highly recommend like trying for like for a next project, just try to do it in GDSFactory, and I think it will be more productive. Like I used to not like layout. Now I like layout because it kind of makes it like fun. It's almost like a video game. You're just drawing polygons and sticking things together and writing simple functions that do things well. And we also have a lot of like advanced functionality that can show you how to do like complicated routing. And for example, we have routing to avoiding obstacles. So this looks like a maze. And it goes like this. Or we have also routing to electrical connections, where you can also automatically avoid obstacles. So we have ways to, when you connect into paths, you can have things like, I don't know if I have an example here. I think it's maybe here, routing without collisions. Yeah, we can do things like this where you can go around. And you can, like if you have these kind of problems, by just passing the boxes of the obstacles, and you can grow the obstacles to avoid like even larger keypad areas. So yeah, it makes it very convenient to do complex shapes, and they're all based on like small function. Like you can see, just a few lines of code, you do like a complicated non-Manhattan router, or like a bundle of many routes, just like a few lines of code. And yeah, any more questions?
If anyone has any questions, either you can send it in the chat or raise your hand. Last questions.
I have a question. Actually, I've seen your metal routing. Do you have also some rounding of the corners that one can easily implement, or is it?
Yeah, we have two types. So like the metal rounding, yeah, you can do metal rounding with RF type corners, or they can do like optical like rounding as well. Like We even have a automatic like bundle router with obstacle avoidance too. So this is that one is a bit slower because it will basically needs to recompute. So you can move the instance in the middle and it will avoid the obstacle. And this has you can define the routes as with pens. So, and you can also modify the parameters of the route. For example, we did this lattice filter before. If I look at the schematic and the layout, I can edit the route. And if I press E, I can define how this route I want it to be. Like by default, this PDK has a cross-section radius, but I can make it larger. I can make 20 at the radius. And you see, because if I make 20, it doesn't have enough space to route to fit 2 bends. If I move it to the right, it will be a bit more direct. Or I can make it even bigger. So now I can make even like 50. You see, 50 doesn't fit. So when it loops into itself, it means that it doesn't really fit. But now it fits 1 bend and 2 bends. But for metal routing, we have, for example, this MZI with pads. You can define like connection to, we're using this route bundle. And then when you define a route bundle, you define like what layer you want to route. So it can be RIP C-band, RIP O-band, strip C-band, strip C-band with a header. So you can route with any of the layers on the cross section, but it needs to have, like for example, let's say I try to route with strip, and then this will turn into an error. So you see it turn red. It's not possible to route metal ports with an optical waveguide. And this is where it's kind of like very nice to be able to define like routing. So I save it, and now it's go back to green. So all these checks help you a lot, like make sure everything is green and you have no like errors. And I can show the GDS so you can see side by side what you have. And the nice thing of this is that as you're making a circuit, you can define like input and output ports, and you can also have input and output ports, and then you can simulate it too. This will be kind of like a Mach sender with a heater. Yeah, I don't know. This one maybe, yeah, you can see the 2 Mach senders. And if you put this into a notebook and then you excite the heater ports, you will see something like we have in the tutorial for this, where we show the SAC circuit simulator with a phase shifter. As you apply some heat, you will be able to change the MCI as a function of voltage. Did I answer your question, Mateo? Nice seeing you.
Yeah, sure. So basically, you can use any type of routing also for the metal, so even bends and everything. Okay.
Yeah, you can do like bundles too. Similar to this N by N chiplets that we were showing before. Yeah. This could be metal routing bundles.
Yeah. Okay, good. Thanks.
And they will follow. Like this is kind of like the nice thing. You can follow. You can rotate. Can make as complex as you want. You see, it just needs to be a possible route. Like if you trick it, it will fail. But then you play with it until like you're happy with it. See, like I can trick it to fail, but yeah. This is where the connectivity comes in handy. Like if you make impossible things, like for example, let me move this one here. This is where connectivity will be very useful. DRC check connectivity, and it will catch it. So you don't have to worry. Like here is very obvious because there's only 4 chiplets. But if you have hundreds or thousands of rules, like good luck at finding these kind of things. Some foundries implement this as DRC. Some others don't. So we have this as a separate check built in. Then you can fix it and then run again. And this is the nice thing, like when you run again, it's similar to what we show in DRC, where we fix one thing, check again, and then see if no connectivity or fixed. Yeah, it's fixed. There's no more. There's some. We also check for things like, for example, in this lattice filter, this looks like correct, but actually it's not. It has a gap here. It has an unconnected port that can cause reflection. So this is also something that connectivity check will check. If you have, as Chonghua was asking, I think the gaps, the 1 nanometer gaps, that if you don't do what we recommend you will still have them. You will get errors similar to here. You have a port that's basically orphan. It doesn't belong to any. You're not exposing it. These ones are exposed to the outside walls. There's an input and output pin, so they don't really flag as orphan port because they are connected as a logical connection in the lattice. But these all three, if you want to really don't connect it to the second stage, you need to terminate it with. We have this terminator, like a spiral terminator, or it could be like a taper that basically radiates the light. If you don't terminate it, this is gonna create reflections, and these reflections are gonna show as ripple on your circuit. So. Okay, yeah, if you don't have any question, maybe we can finish a bit early. Or I don't know if anyone has any more things. Yeah, if you can finish if you can also send the survey, it will help us understand, like, if you had some problems with the installation, we can also improve it in the next workshops. Yeah, any feedback is always welcome.
I have one more question about the bands. So I guess you can either define the bands, especially when they are non-arc. You can have angle step or special step.
Mm-hmm. Yeah,
And
or like you mean like
yes.
like. Yeah, we have different types of bend. So the bend is a bend Euler. We have this
Yes.
P parameter that defines the percentage of the bend that is represented by a Euler. Like if you put like maybe you can show, maybe you can do one that we compare. Like let's just do, let's create a new schematic and I call it bends. And you just put like a B1 bend Euler. Let's just do strip band, then put another one, B2, and then let's just put B3. And they're gonna be on top of each other. And then I look at the GDS. So now we have 3 bends on top of each other. So let me by default, this the bend, let me just go here and I can change the P. So 0, if I make 1 0, it means this is a radial bend. It's an arc bend.
Mm-hmm.
If I do 1, this is a full Euler bend. So let me save it. So you see, so now you see we have a 0 is fully arc, 1 is fully Euler, so it goes from infinite to R back to infinite. But we have the option of making it with a equivalent floor. We have this with arc floor plan equals true or false, that allows you to define if you want to size it by an equivalent radius. So it's R effective is the and so this is an option that you have on the PD case. And yeah, for example, like if you look at the bend Euler implementation, oh yeah, we don't expose it here, but let's say you want to expose this one with arc floor plan, you can modify this component. You put it here. And another thing that is also very helpful, and you can define with arc floor plan, let's say you want to, you're making a PDK, and I say, okay, I'm not very happy with this implementation. I want to have a different implementation, or I want to expose more parameters. You can always go here, create a new Python layout, and I call it my bend, and you just paste it here. And this one is missing this definition, but it's not important. So now I can do show GDS, and this shows the GDS, and I can make another layout as the one we did before. Let's call it bends2, where I'm using my custom bend code to let me show. I think we call it my bend, right? How did I call it? Oh, did I call it?
Yes. Bends2? No.
Bends2, no? Bends2. No, but the Bends2 is the schematic, but how did I call the... Let me go to the PDK image, and I can filter here, bend. Oh, Bends2, yeah. So the Bends2 is the... Oh no, the Bends2 is the schematic. I call it Ben Euler. I call it the same, so that's why I couldn't find it. Just call it my Ben Euler. Otherwise, it basically will be conflicting with the schematic. Yeah. And now I go, it will be conflicting with the PDK. So in Bends2, I can do the same thing as we did before, but now we have the possibility of my Ben Euler, yeah. So I have a B1, we call B2, and we can do a B3 also if you want. Or maybe you can just... And now I can, now you see I have this with RFlow plan, so I can turn this on or off. So if I do a full Euler bend with RFlow plan, compare with a full Euler bend with no RFlow plan, you see that see if the layout shows, the with no arc flow plan is a true Euler bend with no scaling. Like if you do this, the arc flow plan equals true, the effective bend radius, it will be smaller. So if you put, like, let's say this is gonna be like 5, you could do maybe, because to keep the effective bend radius of 5, the bend radius here is going to be tighter. But because you go from infinite to maybe 3 or 4 micron, and then go back to infinite. Yeah, I think you are the expert of bend. So
yeah, no, I was asking if you are a different discretization. Basically, if you have only the spatial discretization, or you have also the angular discretization of a bend. So if you click on the GDS, you check the points, the distribution of the points, if it is kind of a uniform in space or uniform in angle.
Yeah, something I didn't show. You can actually open Layout and sync it. Like we disabled some of the beware options here to don't modify the points. I can bring Layout and we can look at the points. You can do, so this is a PDK setting. So PDK has points per degree.
Okay.
So let me show you here. Like, so what I'm doing here now, I'm gonna just show it in Layout, and this automatically will sync it into Layout.
Okay.
So you can actually, and then
so this spatial uniform, I guess.
Yeah, they're uniform, but this is something that you could customize. So by default, like PDKs usually make assumptions on these things, like. But if you want to customize, let's say you want to make the width of the bend changing, then you may need to do my Euler bend with
Sure. We can define our own. So
yeah, and this is kind of like, we have an example of how to do that, and the sample cross section. So this will show you how to define a custom cross section with different layers and different extrusions, or you could define just as a polygon, like a Yeah, like it could be just like hello world, but we could add here like add polygon, for example, like polygon, and then you can automatically choose the polygon points that you want. For example, like here you can see what automatically completes. So you could add things as polygons too. This is this polygon. You can make it bigger if you want to see more obvious. Like do like a 30. You can see I created a kind of like a triangle. But yeah, like I mean I haven't done as much work in vents as you've done, but like what I've noticed is that depending on the thickness and the material, like the P, the optimal P, if you are tight, if you don't care about space, but if you want to make the smallest bend possible, the parameter, the percentage of the bend that's Euler depends on if it's silicon nitride or silicon, and depends also on the thickness. But yeah, there's also probably there's a lot of papers about bends too. So
Yeah, and then I don't know if you ever met this problem, but this happens if you really want to crank up the number of points of a band for a high resolution. If you want to do very, very low loss, sometimes matters. So basically, you reach the maximum points, and it will start breaking the band in different parts.
Yep.
Have you ever seen any problem in these parts kind of connecting, having kind of small gaps between them? Because we have experienced these kind of things in the past with other tools. So.
Yeah, some of them, when I was in Spain, in Valencia, doing my PhD, we noticed that the number of points affected significantly the beam, the E-beam dosing. So like, we had very different results depending on the number of points.
Yeah, but basically sometimes the GDS kind of it creates multiple polygons because you have so many points that it cannot handle the whole band with a single polygon.
Yep.
And these different polygons sometimes have gaps between them.
Oh yeah, that's the fracturing. That's a mask prep problem. Yeah, like we can do this together. Like let's say, I think by default, let's say we go like now we go 200, and let's go crazy like 2000. At some point, yeah, you're gonna fracture this into. You see if I can. Sometimes the selection, I find it better to show it in layout. So yeah, once you start to have kind of like a
that is kind of typical. Yes.
discretization problems.
Yeah.
And this shows.
But what I was talking about is that if you even put, I don't know, 8,000 there, at certain point that band will not be a single polygon, but you will see, I don't know, try to put 8,000 and see what happens.
Yeah, a fracture. You see.
Yes, exactly. Sometimes in those kind of junctions between polygons, you see there is a gap.
Yeah.
But I mean, it happens randomly. But so I don't know if you have ever seen that or consider how to solve that, basically.
Yeah, I solved this by not putting too many.
Okay.
I think oversampling can create more problems than it fixes. No, I never found a case where oversampling the band will.
Yeah.
But yeah, I've seen this in data prep with tools like Calibre can have these kind of problems.
Okay.
Yeah.
Just checking.
Yeah, but we usually don't even expose this as a parameter, but you actually we have it as a parameter. We usually by default is none. In the same that we can also pass a custom layer, but we usually take the layer from the cross section.
Yeah.
So PDKs usually make some assumptions, but yeah, if you want a custom PDK, yeah, maybe we can talk how to help you separately.
Yeah. Okay, thanks.
Thank you. Okay, I think maybe I think we're almost about time. I think thank you everyone for joining, and thank you Alex for organizing, and there were two Alex. Thank you both Alex, And yeah, hope to see you at the next workshop, and maybe see you in Toronto sometime, or any conference. I will be at Clio next week in basically in LA. So if you guys are there, maybe I'll be happy to meet in person. And yeah, we'll also have more GDSFactory events coming, so you can follow us, and we'll be happy to keep making chip design more accessible to more people and fun and easy. Okay, thank you very much.